and we want to show the impression that can easily be used for the experimental purposes. That means if we use this equation, J equals these things, the sum of these two terms, and we can just do experiments using the pre-edged edge crack plate, and we can use that one and to do the experiments to continuously measure the M. I measure the M value and also omega P value, and then we can continuously calculate the J. Okay, when we do experiments. No, actually, we do not do experiments. So this is just the one to facilitate the calculation of J for these experimental mechanics people. So I told you guys, so this is the reason, okay? And then we talk about J and CTOD. What is the relationship of J and CTOD? We have learned this equation. And the delta, okay, what's the delta, guys? Delta means the CTOD here. Okay, Sharon, yeah. The delta is a CTOD, and G is the energy release rate, and sigma M, sigma ys is the yield strength. M is a value that is around 1. And so for this is a small scale yielding, whenever you see SY, it means that it is small scale yielding. And small scale yielding means that J is the energy release rate, okay? And the same as this is a G there. And also same as the G energy release rate. And so these are small scale yielding. If these are small scale yielding, K, G, or J, and both of them are still okay. Right? But J is okay. J not just for linear elasticity, but also for linear elasticity, small scale yielding, and even on big scale yielding. But when we talk about small scale yielding, so J, G, and K, and all these three guys, they are valid. Okay. However, if the plasticity becomes the dominant, K is invalid, G is invalid, but J is still okay. You should know that. Now we want to consider on how we calculate the G, how we this is the get the G value, how we express the relationship between delta and ys, and between delta and ys, how we relate J with the delta and sigma ys. So we still here we consider a strip yield zone ahead of crack tip. What is a strip yield zone, guys? Can somebody tell me? We talked about the strip yield the model before, and can somebody just remind me? What is a strip yield zone? I'm old. I cannot remember. Cannot recall. Can somebody remind me? Bobby. Try.
It was one method, right?
Yeah,
like
one method.
Several methods to figure out something.
Yeah. Okay, good. This is one method. Okay, so this method means that we just think things reversely. We do not think about on how much energy we need to open the crack. We think things opposite. How do that? What does that mean? It means how much energy I need to close the crack. Okay, guys? I want you to know that, okay? The strip yield zone, it is another approach. And so in this approach, and we want to investigate how much energy it is needed to close the part of the crack. If I know this, then I will know for this original one, okay? Let me show you. So here is my original one. And so here, this one is the bigger one, right? So I want to know the normal thinking process is that I wanted to know, okay? This is A. So here is and A, the dA, A plus dA. So the normal thinking process is that I want to know how much energy I need to open this crack from A to A plus dA, right? Right? I want you guys to follow me. I don't want you guys to do anything else. Let me express this way. If you just use this time, class time to do anything else, you need to use the same amount of time to review the lecture notes, which is the waste of time. What? So I need to repeat. So the normal thinking process is that from crack length A to crack length A plus dA, we want to know how much energy we need to open the crack and to make the crack become bigger. So this is normal press. This is a normal thinking process. The strip yield zone means that what? I just think this one reversely. I'm from here. I want to see how much energy it is needed for me to close this dA so I can get this crack length from here. What? So this is a strip yield zone. So here it says here. So this is my original crack length, crack tape. So here is my new crack tape. I want to know how much energy, okay? How much energy I need to have to apply and to close. So this one. Understand? So you can see, okay, so using the actual face, so you see now here. So this is my new crack. This is my crack. I want to know how much energy I need to apply, and so I can short. This is a crack length from B to A. So get this new crack tape. How much energy I should have? So you can see, this is what I labeled here. Alright. So this is the crack face, and suppose I have traction there. Now I do this J integral, and this is J integral, and this is a crack tape. So this is this is a crack tape, okay? So this is a crack tape. I want to see how much energy, and this is a J integral, and for this one, the crack tape is here. Now, I showed you guys, and for this is when we calculate the J integral, so the J integral is independent of this is a contour, right? You still remember, guys? The J integral is independent of the contour, the gamma, the path, right, guys? Yes. So if this is independent, I can select any, and this is the path. Now this time I'm going to select the path, from this is A, and to B, and then to C. As long as this contour it is counterclockwise, right? This is the J value. This is J value. I can use this one and the contour. I know that. And for this, I have this contour from A to B to C. I have two segments, and one segment is from A to B, and second segments are from B to C. Right, guys? And then for the AB, and I just follow this equation, okay? So for AB, I have first term, and this is a T, this is TUY, okay? So this is TUY. And look at it here. And for this AB here, guys, and for this AB, from A and to B, I need to tell you, so this is the crack is very sharp crack. The sharp crack means that, so this A and B, we can assume they are on the same horizontal line. If they are on the same horizontal line from A to B, and the Y does not change, right? Right? dy is equals 0. And then if dy equals 0, I do not need to take care of this is this omega. Omega is energy density, straight energy density, right? I don't need to say that this guy equals 0. And then I look at the second term. And second term, this I here, I is the I appears twice. Appears twice means this guy is a dummy, right? Dummy means summation. You guys agree? So that means this is Ti and Ti multiplied by and dui and dx. Ti dui dx. So I is a dummy. Yep. So this dummy means summation, and summation means that if we just expand this one, it equals T1 multiplied by du1 dx and plus T2 multiplied by du2 and dx, right? So this I is a dummy, I is a dummy, and dummy means summation. What is the summation? And summation means that and you let I equals 1 and 2 and for 2D. Right? 1 for 2D, that means when I equals 1, I have T1 du1 dx. Then plus is a summation sum. T2 du2 dx. Right? Okay. Now look at here. Look at on this is a crack face. I have this. So this is my sigma ys. Okay, so this is my sigma ys. So this strip yield zone means that I just apply the yield strength on this is the extra crack length to see how much energy I'm going to need to close that part. So this is sigma ys. The sigma ys. Okay, so for here, so this is x. So this is the y. So this is the 1 means x and 2 means y. So T1 here and T1. So T1, so this is the n value. N equals 0, 1, right? N is the normal. Normal for this is lower crack face. This goes up. And so this guy equals 0, 1, right? So the T1 equals and sigma let me see, sigma I, Ty equals sigma ij, the comma j, right? So T1 equals and sigma. Now J is a dummy now. J is a dummy. Dummy means summation. And it equals sigma 1, sigma 1, 1, n1 plus sigma 1, 2, n2. Right? I know that. So this is sigma 1, n1 equals 0, and n2 equals 1. So for this is on this surface, I only have sigma ys, on which equals on sigma 2, 2. Okay? Sigma ys is going up. Right? So as a result, on the sigma 2, 2, I only have sigma 2, 2 here. So this is this equals 0. I don't have sigma 1, 2. And sigma 1, 2 is a shear stress, right? And sigma 1, 2 equals 0. As a result, T1 equals 0. Right? Then T1 equals 0. So I don't need to take care of this one. And then we can look at the T2. What's the T2? And T2 equals sigma 2, 1 multiplied by N1 plus sigma 2, 2 multiplied by N2. Right? So N1 still equals 0, and N2 equals 1. But if this guy equals 0, and so this whole thing goes away, and sigma 2, 2 is the sigma ys. So this is the sigma ys. So this equals sigma ys. T2 equals sigma ys. Right? So here, come here. So this equals 0, and then I have T2 and du2 dx, and so this T2 equals sigma s. I have sigma ys multiplied by du2 and dx. So this is how I have here. And du2 means duy, right? And du2, this equals sigma ys and duy and dx. You understand? Okay, this is how we get this, how we go from here to here. Right? Now, the same thing for this one, the same thing for this one. But this one, so this is the BC, this is the BC, this is the B and the C. So now this time, this is my stress. This is my stress, sigma ys, sigma ys. So also now this time, this n equals going down, 0 minus 1. Right? And then you can just still use this equation and go through this process, and you will have sigma ys, and now dy uy dx ds. So this ds is arc, the arc increment. The arc increment is from this arc. So this is ds. Next one. Okay.
Why is it negative and one is positive? Like,
Here.
yeah, so it's negative sigma s in there, but we derived it as a positive, like.
But here is a original, here's a 0 with minus.
Okay.
Here's a minus. Right? So this is a minus, but itself has a minus. So the minus cancel another minus. Good question. Question so far? No question. And then on AB, okay? You can on AB. On AB, the straight line, horizontal line, and I just for exaggeration, I just draw this one B. Horizontal line from A to B, ds, okay? ds equals negative dx prime. Do you guys agree? Now, and this x prime goes to the left. Usually we go to the right, right? But now we change x prime. And why we want to use x prime? Because so this guy, the BC is going to the left. We want to unify them. You understand? We want to unify these two lines. One is going this way, one is going that way. Okay, so ds equals negative dx prime, and for our BC, ds equals dx prime. Do you guys agree? Okay, so we just change the ds to the dx prime. So this is the dx. We know dx equals dx prime, and this dx equals dx. So we have positive side here. So this is negative. So this negative and cancels this negative. So as a result, we have sigma ys duy dx prime plus BC on BC sigma ys duy dx prime. Any questions from here to here? No question, right? No question? And then we look at uy. Okay, and even though this guy is a very, very sharp, is a very sharp one, okay? Very sharp one. So this guy we just assume. So on this edge, on A, B, and C, for A, B, this displacement, we say it is going down. It is Uy and minus, okay? Uy minus. And for the points on the BC curve, and we see on Uy and positive. Is one is positive and one is negative. And we can just imagine. So if we have a very, very sharp crack, right? But still, so these two surfaces, they can be treated identical, but if there is some traction there inside, if some traction, we still can know that there is some displacement, even though the displacement is very, very tiny. You guys agree? You guys agree? Okay, and then we look at the next step. And we know that, and if we just do the integration on a line, okay, so this line, it is directional. And then we change, you can see, we change the order. See, guys? AB to BA, and then there's a minus sign here. Right? There's a minus sign. From AB to BA, and they are positive. Still remember, guys? If you don't remember, let me give you the hints. You can see, guys, still remember the calculus from A to B, okay? The something, and this is a dx dy. So this equal, I'm sorry, this is 1D. So this equals minus from B to A, the same integrand dx. Do you guys agree?
Yes.
If you change the lower limit and upper limit, reverse it, and you need to put a minus sign there, right? So this is what we have learned in the calculus. So that's the reason we change here. Why we need to change here? Because AB goes to the right and BC goes to the left. This is not good. I cannot unify them. In order to unify them, I need to make sure so this line segment and that line segment, they have the same direction. Okay? So I have BA, they have BA here. I have the minus sign here. It's a BC. Now, BA and BC, both of them are going in the left direction. So as a result, I can put them together, okay? BA and BC, and they are the same, identical. BA goes in this direction, and BC goes in this direction. The same direction. As I said, so this is the displacement is very, very negligible. It's very, very small. So as a result, I can put these two integrands together. And then I have both of them, they have sigma ys. Then I have this value here. I have this value, and then I have dx. Are you okay with this step? Okay.
Yes.
Okay, now this is dx, okay? These are both of the dx. Now I can put them together and put these two guys together. Sigma ys and d, okay? So this is d, so these two terms within these parentheses, and we can rewrite them as d, right? And now uy plus minus uy minus and dx. You guys agree? Now, if I put them together, what is the uy plus minus uy minus? Uy plus is the displacement on the top edge, and uy minus is the displacement on the lower edge, right? So what's the difference between these two guys? The difference between these two guys is how big you crack open. You have sense? So that's the reason we can have delta. So this the difference between these two guys. The difference between these two guys is the delta. The crack opening, how much the crack opens at the tip. So this is delta. See? Okay, so this is the dx prime. So this is dx prime and dx, and we can just this is d delta. So we can this guy cancels this, and we can have sigma ys and delta d delta. This guy cancels this.
So those are the same, like dx is equal to dx prime?
Yeah, there's a minor sign there, but it does not matter. Okay. Huh? That's a good point. That's a very, very good point. Thank you, thank you. You understand? Okay, so and then you can see here, we can the sigma ys is the yield strength, and we just take it out. And from 0 to rho, and from the rho is the prevalence from here. This is rho. This is the rho. And it equals delta T at the tip. So here is the rho, right? From this tape to this tape. This is rho. You understand, guys? Then J equals and sigma ys multiplied by delta T is the tape. The crack tape, the displacement, opening displacement and the crack tape. So this is Dr. Shin's the J-CTOD relationship. And J is related to the delta. Delta is the CTOD value. And this is strip yield zone. This model gives us. And Shin, Professor Shin's relationship between J and CTOD, and they use the HRR the model. Delta equals so dnj and d sigma 0. Sigma 0 is the reference, the stress, and it's usually equals sigma ys. So dn is a dimensionless constant. Dn is dimensionless constant, and dn is written using this equation. Right? So some students might ask, Donna, which one is correct? I would say both of them are correct. And we should ask which one is accurate, more accurate, with depends. It still depends. Questions? Guys, do you like this kind of derivation? Huh? Yeah, I want you to know this derivation, okay? Because this is senior students and also some graduate students. I want you guys not just know the equations, but know how to derive these things. And this one can help you a lot. Also, by the way, fractional mechanics is also 800 course in the research university. Questions so far? The mass, you can see how important the mass is. Without the mass, and we just scratch the surface, we cannot dive into the water. Right? Even though we see, and there are a lot of the treasure boxes and the water, if we do not know the mass, we cannot get it. We cannot get these treasure boxes. You know what I'm saying? Without the mass, we just splash the water on the surface, which flows on the surface, we cannot dive. And even only after we know these derivations, and we will know how to get these treasure boxes. Right? You know the mass is extremely important. And especially when you clear, as your career advancement, as your career advances, you need to know the math more and more. Questions so far? The relationship between J and the CTOD. The relationship between the J is integral, and CTOD is the crack tape opening displacement. And then we talk about on the crack growth, the resistance curve. The crack growth resistance curve. Now look at this curve, this one. And we know that when we talk about the energy release rate, right? And we also talk about this R resistant curve. You still remember? So this is the same thing, very similar. But now, as you see, for linear elasticity, guys, this is on what we have learned. So from the initial, the crack length, the TC, TC is a critical energy release rate, and R is this is the resistance curve. If G is greater than R, and so this crack is going to propagate, right? So this is what I told you when we talk about the linear elastic fracture mechanics. Now, because we have learned more, and we talk about J here. You can see J is also, when we compare these two curves and these two photo figures, and they are quite similar. So you can see here. So this is because of the elastoplasticity, and this crack tape, and when this is the crack, before it propagates, it becomes Brantoning first. Okay, you know Brantoning, right? Guys, do you know Brantoning? So here, so this is my original crack. It's very sharp. As the load increases, it goes this way, right? Go this way means as a blending, but the crack table is still there. Crack table does not change. But only after this blending, and when it reaches some value, it cracks. The crack propagates. So this is actually how the material behaves if you keep improve the loading. So you can see at the very beginning, if the JR is this is JR resistance, okay? If the JR is higher than the JIC, it starts initiation, as we have here, until so this guy reaches this is the steady state. So this is the constant is slow. This is a DGR resistance. R means resistance over dA. Okay, so for GR curve, instability. Instability means after you reach this point, you cannot control the crack propagation, crack growth. So when J equals GR, J, okay, and this J value is dependent upon your loading condition. Understand, guys? This J is dependent upon your loading condition, and this JR is the resistance J of your material, which is material parameter. So if this guy equals each other, and also the increment of J equals this increment of JR, and so this is unstable. It will propagate until the whole piece breaks. So here is one value here, TR, and TR is written as DGR dA E sigma 0 2. And as I said, sigma 0 here, and it is the reference stress value. It usually equals the yield strength. If you have not written this down, I would suggest you write this down. Okay? So sigma 0 is the reference stress value, and it usually equals the yield strength sigma ys. So this one, so this term is called theorem modulus. So TAPP, okay, so this is, we also have TAPP, this application applied. this applied theorem modulus, and we compare TR and TAAPP. So it's the same thing, and when we compare J and JR. Questions? So you can see, for this instability in load control, this load control is unstable. Once it is happens, so as you can see, usually this one, the slope of this is higher than the slope of this curve, this R. So this is usually for load control, it is unstable. So stable, this is when these two, J equals JR and TAPP is greater than TR, so this is unstable. And however, when J equals JR, however, TAPP is less than or equal to JTR, it is a stable crack growth. And for this is low displacement control, it usually is the stable crack growth. Okay, that means if this condition is met, you have crack length, the crack growth, but then you stop. The crack will stop. You have that? Bobby, did that make sense to you?
Yes, it's very similar to the other linear elastic.
Yeah, very similar. But now this time we use J instead of the G. What? Questions so far? Okay, no question, and we switch our gears to the lecture 16. And I want you guys to know this one. Okay, in the final exam, I might ask you guys to tell me something. If I draw the figure, and I might ask you guys to use your own language to tell me, and what condition we have unstable crack propagation, and what condition we will have stable crack propagation. You should be able to figure out what I'm asking. Alright, this is answers. Then we switch gears to lecture 16. Let's say, so then we talk about J, and we have used a lot of time talking about the J integral, and now we talk about J controlled fracture, right? So J can be used to completely characterize the crack tip condition. So in this case, and J equals is interchangeable, and J is not equals, I should not say equals, because based on the values, they are not equal to each other. But on J and CTOD, and they are interchangeable. You can either use J integral or the CTOD and to describe the crack tip conditions. So J controlled fracture implies the CTOD controlled the fractures. So however, so it says that the fracture mechanics analysis based on the J and CTOD becomes suspect where there is excessive plasticity or significant crack growth. So that means J and CTOD and also is only valid under some conditions. Okay? So in such cases, our fracture toughness and the JCTOD relationship dependent upon the size and geometry of the structure and the test specimen. I want you guys to underscore this statement and know that J and CTOD, they are also have some conditions to be valid. Outside this boundary, it is not valid. Okay? And then we talk about here, can see here. For small scale building, and for small scale building, and so you can see for small scale building, right? For small scale building, this we have K dominated zone. This is K dominated zone, the whole thing. This is J dominated zone. So this is the large strain zone. If the strain is large, this is a largest strain zone. So here, so there's no single parameter. So here, no single parameter characterization. But within this area, so we can use K to describe. And within this area, we can use J to describe. So this is the small scale building. For small scale building, you can see here, okay? So this is sigma YY goes up. So this is log R/2. So this size of the structure, and here, so this is logarithmic the figure. So this is HRR. So this is LEFM. So this is for this area, and we can use LEFM. For this area, and we use HRR to describe. Okay, I'm going to stop here now, and we can finish this one by this Friday. Any questions before we end today's session? No question? Okay, no question. I would say have fun with the exam. Yeah. I don't get what you said. You say again? Yeah. So this is not our. This is an account. It's not our. Where we need to get this number? Where we need to get this number? UI and UI. Which one? I forgot. Our quiz, right? Our wallet. And what you said? Can you say again? Problem solution. Well, can you do you have the quiz? The quiz.
And also, you want to grab just this one, make that like the signal one.
Yeah, don't use this one. This just tell you how to use answers.
Yeah, okay.
But just follow the questions I asked in the quiz.
Okay.
What? Yeah. A question, Dylan.
Yeah.
Yeah.
I think it's all like
Yeah.
it's supposed to be like a 25mm crack and then 25.
Yeah, I told about this one. Just 1 second. Let me. Hey, sorry. Oh, can we meet later?